269 degrees Celsius. That is colder than outer space. And just a few meters away from that, 150 million degrees. 10 times hotter than the core of our Sunday, both of those extremes exist inside one machine. At the same time, and 35 nations are building it right now in the French countryside. Welcome back to the channel. Today we are covering one of the most complex, most ambitious, and most consequential engineering projects ever attempted by human civilization. It is called ITER. And if it works, it changes everything. This is not just a very large magnet in the south of France. It is a machine designed to recreate, in a controlled way, the same physical process that has powered every star in the universe for billions of years. It is a machine where the interior must reach temperatures that no solid material on Earth can withstand, where the magnets must be chilled to the coldest temperatures achievable in any laboratory, where components built on 5 separate continents by 7 different members representing 35 nations must fit together with tolerances measured in fractions of a millimeter. And it must do all of this simultaneously, continuously, without failure. Because if any single system fails, there is no fusion. Imagine the entire effort of the International Space Station, the international cooperation, the precision engineering, the years of construction, and then scale it up by an order of magnitude. Then bury most of it underground. Then make it radioactive. That is ITER. Before we go further, make sure to subscribe to the channel. If you are watching this, you care about how the world actually gets built. We cover engineering at the scale where it becomes almost impossible to believe. And stay with us until the end of this video, because what the workers at ITER see every day and what the rest of the world almost never hears about is one of the most extraordinary stories in the history of construction. At first, there was only a rocky plateau in Provence, a flat man-made shelf of ground, 1 kilometer long and 400 meters wide, roughly the area of 60 football pitches, carved out of the hills near the Durance River in southern France, not far from Bercy. No buildings, no roads capable of carrying what would need to come, no infrastructure suited to the task. Just heat, limestone, lavender, and the distant hum of the Cadarache Nuclear Research Center next door. The year was 2006, and the 7 members of the ITER consortium had just chosen this site, France beating out Japan as the home of the most ambitious physics experiment ever conceived. The first problem was this: how do you build a machine that has never existed before? There are no precedents for ITER. There are no construction manuals. There is no company on Earth that makes fusion reactors. Every single major component of ITER had to be invented, engineered from scratch, tested, and manufactured for the first time sambiensely across 12 time zones, in factories that had to be retooled or purpose-built by workers who had to learn techniques that did not exist 5 years earlier. If you tried to build ITER in one country, no single nation's industrial base could supply everything it requires. If you tried to build it with standard commercial procurement, the tolerances involved some components must be positioned to within a millimeter across a structure that weighs thousands of tons, would make cost and schedule impossible to guarantee. So the solution was not simple. It was a global assembly line unlike anything ever organized, in which each of the 7 member entities, Europe, China, India, Japan, South Korea, Russia, and the United States took responsibility for fabricating specific, defined pieces of the machine and shipping those pieces to one point on the Mac, a plateau in the Provence hills, where a workforce from more than 90 countries would then attempt to assemble them into something that could hold a star. Then came the site itself. Before a single component of the Tokamak could be installed, the ground had to be prepared. Site preparation began in 2007, 3 years before official construction started, with the clearing and leveling of the 42-hectare platform. The limestone bedrock was blasted and graded. Drainage systems were installed. Electrical infrastructure was laid. Access roads were built. And then, from August 2010 onward, the buildings began to rise. This was not a question of pouring some concrete and raising some steel. Every building at ITER is a precision instrument. The Tokamak building, the centerpiece, sits on a seismically isolated foundation. Hundreds of anti-seismic pads support the entire structure, giant rubber and steel bearings capable of absorbing the energy of an earthquake and protecting the machine inside from even the slightest ground movement. The foundations reach deep. The walls are thick. The structure must be stable, not just against earthquakes, but against the internal forces generated by the machine itself, forces produced by magnets storing 51 gigajoules of energy, equivalent to the kinetic energy of a fully loaded aircraft carrier moving at speed. Every decision mattered. Every cubic meter of concrete mattered. The Tokamak complex, the cluster of buildings at the heart of the ITER site, took years to complete. The central Tokamak building was finally handed over to the ITER organization in March 2020, marking the official start of machine assembly. That handover was a milestone, a decade in the making. Then came the components. This is where ITER's engineering story becomes something almost surreal. Because the machine does not arrive at catenage pre-built, it arrives in pieces. Enormous, breathtaking, impossibly heavy pieces, manufactured on the other side of the world, loaded onto ships, sailed across oceans, unloaded at a Mediterranean port, transferred to barges, floated across an inland sea. That road is called the ITER itinerary. It is a 104-kilometer route stretching from the port of Fos-sur-Mer on the Mediterranean coast west of Versailles, through 16 French villages, across 35 bridges, around 19 roundabouts, to the gates of the ITER site. France spent approximately 112 million euros preparing it, widening 35 kilometers of route, reinforcing bridges, redesigning roundabouts, and in some cases creating entirely new stretches of road, just so that convoys of extraordinary dimensions could pass through. Convoys weighing approximately 800 tons, including the vehicle. Convoys up to 10 meters tall, up to 33 meters long, up to 9 meters wide. Convoys escorted by the gendarmerie, traveling at walking pace, crossing motorways closed to traffic, squeezing past old stone walls at 5 kilometers per HR. While villagers lined the streets to watch in the early morning darkness, every convoy traveled at night. Approximately 250 such convoys were planned across the life of the project. Each one was a unique engineering operation. Each one required weeks of preparation, coordination between transport company, Daher Agence ITER, France, and French public authorities. Each one moved components, the magnet coils, the vacuum vessel sectors, the cooling systems that had been years in the making on other continents. Take the toroidal field coils. These are the 18 massive D-shaped superconducting magnets that form the core of the magnetic confinement system. Each one stands 17 meters high. Each one is approximately 9 meters wide. Each one weighs roughly 310 tons, about the weight of a fully loaded Boeing 747. 8 of these magnets were manufactured by Japan. 10 were delivered by Europe. Each required years of winding, insulating, impregnating with epoxy heat treating, and testing in dedicated facilities before being cleared for shipment. They are made from niobium tin superconducting cable, a material that carries electrical current without resistance, but only when cooled to approximately 4 Kelvin. That is minus 269 degrees Celsius, colder than deep space. This was not a simple fabrication challenge. This was the creation of the largest integrated superconducting magnet system ever built. The 10,000 tons of magnets, toroidal field coils, poloidal field coils, correction coils, and the central solenoid arrived from factories across the globe, the toroidal field coils from Japan and Europe, the poloidal field coils wound on site in France and contributed by Russia and China, the correction coils from China, and the central solenoid from the United States. The central solenoid alone stands 13 meters tall, 4 meters wide, and weighs 1,000 tons. It is ITER's backbone. It is what drives the plasma current inside the machine. Japan supplied 43 kilometers of niobium tin superconductor strand for its construction, which was then wound in the United States. Every strand mattered. Every winding mattered. Every cooling channel mattered. Then came the vacuum vessel. This is the donut-shaped chamber, the torus where fusion will actually happen. It is made of 9 sectors. Europe manufactured 5. South Korea manufactured 4. Each sector stands 12 meters high, is 6.5 meters wide. Welded together, the complete vacuum vessel will weigh approximately 5,000 tons, comparable to the weight of the Eiffel Tower. Its walls are double-walled with internal cooling channels. They are made from a special grade of stainless steel, capable of withstanding the extraordinary thermal and radiation stresses of a fusion plasma. The vacuum vessel must also be a vacuum, not merely low pressure. A hard vacuum equivalent to 10 to the power of -4 pascals. A vacuum more perfect than what you would find on the surface of the moon. Any contamination, any impurity in the gas and the fusion plasma collapses, any breach of the vessel wall, and the experiment ends. There is no tolerance for imprecision. Then came the cryostat. This is perhaps the most staggering single component of the entire machine. The cryostat is a vacuum-tight stainless steel shell that completely surrounds the vacuum vessel and all the magnets. It is the world's largest stainless steel vacuum pressure chamber ever constructed. It stands nearly 30 meters tall and nearly 30 meters wide. It has a volume of 16,000 cubic meters. It weighs 3,850 tons, and it was manufactured in 54 separate segments in India, shipped to France, and assembled on site in a purpose-built 6000 square m workshop by the Indian Domestic Agency. The cryostat is ITER's thermos flask. Inside, the magnets must be maintained at 4 Kelvin. Outside, the ambient temperature of the French countryside varies with the seasons. The cryostat provides the vacuum environment that makes heat transfer between those two worlds almost zero. Without it, the magnets cannot achieve superconductivity. Without superconductivity, there is no magnetic field strong enough to confine the plasma. Without the magnetic field, there is no fusion. The chain is absolute. Every system depends on every other system. The chain of dependence runs throughout every corner of the machine. The magnets need the cryostat. The cryostat needs the vacuum pumps. The vacuum pumps need the electrical systems. The electrical systems need the cooling water system, a network of pipes carrying hundreds of tons of water per hour to extract heat from every part of the facility. India contributed ITER's cooling water system. Without it, nothing can operate. Then there is the cryogenic plant, one of the largest in the world, which produces the liquid helium and liquid nitrogen needed to cool the magnets. There is the radio frequency heating system, the mechanism by which 50 megawatts of external power will be injected into the plasma to bring it up to fusion temperatures. There is the tritium fuel handling plant. There is the remote handling system, because once ITER is operating, the interior of the machine will be radioactive, and all maintenance must be performed by robotic arms operating under remote control. Millions of individual components. The ITER organization estimates approximately 1 million parts in the Tokamak alone. Hundreds of thousands of assembly tasks planned and sequenced by teams of engineers from dozens of countries, coordinated across language barriers, across time zones, across political tensions that on occasion threaten the project momentum entirely. The total estimated cost of ITER's construction phase, which began at roughly $10 billion in original projections, then rose with revised schedules, now stands at approximately $20 billion or more. The timeline has shifted significantly. The original plan called for first plasma in 2020 and full deuterium. Tritium operation by 2025. Those dates are long gone. The current plan, known as Baseline 2024, targets start of research operation in 2034, with experiments using burning plasma, the full fusion regime, planned for approximately 2039. The delays have been caused by a combination of the COVID-19 pandemic, technical discoveries that required design changes, including critical decisions about the materials facing the plasma, the extraordinary complexity of coordinating a global supply chain, unlike any that has existed before, and the inherent challenge of engineering at the absolute edge of what is physically possible, and through all of it, assembly has continued. The cryostat base, all 1,250 tons of it, was lowered into the Tokamak pit in May 2020, the first great act of machine assembly. Then, over the following year, the installation of the lower cryostat cylinder, the placing of the central solenoid modules, the delivery and positioning of vacuum vessel sectors arriving from Korea and Europe through the ITER itinerary in the darkness of Provençal nights, the installation of correction coils, the connection of magnet feeders, those multi-lane conduits that deliver both electrical power and liquid helium to the magnets simultaneously. The assembly has involved work at every level, from the seismically isolated bassimat deep below grade, up through the machine itself, to the top of the Tokamak building rising above the Provence plateau. The scale of the workforce is equally staggering. At any given time on the ITER platform, close to 5,000 people play a role in the ongoing machine and plant assembly work packages. Most people who will one day read about ITER's achievements will only see the headline. They will see a number 500 megawatts. Q equals 10, 2039, fusion. They will not see the 352 wheels of the transport trailer inching through a French village at 3 a.m. with a magnet in tow. They will not see the welder in a facility in Japan spending weeks on a single joint in a vacuum vessel sector, knowing that joint cannot be done once the sector is assembled. They will not see the engineer in South Korea calculating the stresses in a cryostat segment under conditions that no engineering code had previously covered. They will not see the Indian workshop on the ITER platform, where 54 stainless steel segments were painstakingly cleaned, fitted, and welded into the world's largest vacuum chamber. They will not see the technician in the United States carefully winding kilometer after kilometer of superconducting cable around the central solenoid coil packs, knowing the tolerances are so tight that a single error in winding geometry. They will not see the meetings, the thousands of technical meetings, management reviews, council sessions, scheduled negotiations that took place between 7 member entities. Across decades, as the ambition to recreate a star was slowly, painstakingly debated and refined and defended and funded and kept alive. Without that web of human effort, there is no machine. With it, if the physics works, if the engineering holds, if the plasma burns, there is a new answer to the oldest question energy science has ever asked. There is something almost philosophical about what ITER represents. The Sunday has been fusing hydrogen for roughly 4.5 billion years. It does not need our help. It does not need our equations, our magnets, or our superconducting cable. It burns because gravity is so immense and the density of matter at its core so extreme that hydrogen nuclei are forced together continuously, releasing energy in quantities so vast they are almost without meaning at human scale. We cannot replicate that gravity, so we have done something more extraordinary. We have found a different path: magnetic confinement, temperatures 10 times hotter than the Sunday's core, engineering precision that barely existed a generation ago, and we have gathered the industrial capacity of half the world's population and pointed it at a single plateau in the French countryside and said, we will build this. Not because it is easy, because the alternative is to leave it unbuilt and to live with all the consequences that flow from that choice. ITER will not generate electricity. It is an experiment. It is proof of concept. But proof of concept is the necessary step before the first commercial fusion power plant. And that step right now is being assembled sector by sector, coil by coil, weld by weld in the south of France. If you found this video remarkable, please subscribe to the channel. We cover mega projects exactly like this, the ones where the engineering reaches the edge of what human beings have ever attempted. Leave a comment below. Do you think ITER will eventually prove that fusion is feasible? We read every single comment. Thank you for watching.